Okay, question 4 is about magnets and magnetism. So we can see we've got a magnet there and it's picked up the paper clips. So we know that'll be a south pole, north pole, south pole, north pole, and it tells us that there, south, north. So that makes loads of sense. We know that the magnetism on the paper clips is temporary. It's only there when the magnet is there. Take it away, there's no magnetism, and it's induced magnetism. So if I've got a magnetic material, I've got my magnetic domains, and at the start they're all lined up in different directions. But if I magnetize it, I can then line them all up so that they go the same way, and that's what we've done with these paper clips. We've lined all their magnetic domains up so that they're going like that. Okay, so now let's have a look. Label the poles of the other two paper clips. I've done that already. Okay, so done. Next one, complete the sentence by choosing the word from the box. These paper clips have, well, we're after the word temporary or induced. There we go, induced magnetism. Suggest a material, so any magnetic material. So iron, if you put in there soft iron, that'd be fine. Nickel, cobalt, steel. Now, the difference between, say, soft iron and steel, this will maintain its magnetism for longer. Soft iron will lose it more quickly. So in terms of electromagnets, that is a better choice. When the paper clips were pulled off the magnet, they fell separately to the table. How could you test if any of these had kept their magnetism? Well, if I wanted to, this isn't going to be in my answer I give. I could try to see if it deflects a compass. But the nice way is, well, I need something smaller than paper clips that's magnetic. So I could just take iron filing sprinkler, sprinkle it over, and then if there's my paper clip, see if I've got a magnetic field. Butterfly, butterfly, straight, curve, curve. Or get a pile of iron filings and see if my paper clip attracts them. So any of those. But I think the crucial part is we're just saying, well, pick something that's magnetic but smaller and see if that then attracts. So see if the paper clips attract iron filings, or sprinkle the iron filings and see if there's a pattern around the clip. Here we've got the magnetic field, so we know that we have to use the right hand grip rule. So I would get my right hand, I'd point my thumb up and then have my fingers going that way and then wrap around so I can see that it goes like that. And we know that the spacing increases because the field is stronger here and weaker here. And that's because the magnetic field lines are closer here and they're spaced further apart here. Or this has a higher magnetic flux density. So there's all the basics. Let's get rid of all of that stuff there. So how can you tell the strength of the field is greater at P than Q? The magnetic field lines are closer together. All right, so the magnetic field lines are closer at P than Q. Or you could be really fancy and show off. There's a higher flux density or magnetic flux density at P than Q. Next one, the magnetic field strength is measured at P for different values of current. And we can see this here, so we're increasing it. We can see we've got a straight line and we've got this in microtesla, but I don't need to do any calculations on it. Describe the relationship. Well, as that goes up, that goes up. We don't use the words goes up and goes up. We use the words increases. So as current increases, magnetic field length increases, and it's that same old question, then talk about the pattern. This is a linear or directly proportional relationship.